When we look up at the night sky, we are naturally drawn to the profound question of whether we are alone in the universe. For decades, our search for extraterrestrial life has focused primarily on planets that resemble our own world. We have sent rovers to scour the arid, dusty surface of Mars, hoping to find fossilized microbes or remnants of ancient rivers. We have peered into the thick, toxic atmosphere of Venus, and we have searched for exoplanets orbiting distant stars in the habitable zone. Yet, as our understanding of planetary science has evolved, our attention has shifted toward a completely different type of celestial body. We are no longer just looking at rocky planets. We are looking at icy moons, and one moon in particular has captured the imagination of astrobiologists more than any other. Orbiting the largest planet in our solar system is a world wrapped in a shell of cracked ice, hiding a deep, dark secret beneath its frozen surface. That world is Europa, the fourth largest moon of Jupiter, and it is widely considered the most promising place to look for alien life in our solar system. Long before the invention of the telescope, ancient civilizations from Greece and Egypt to Palestine, modern-day Israel, mapped the stars and planets, recognizing that there was a grand clockwork to the heavens, even if they could not yet see the complex worlds above them. The true nature of the planets remained entirely obscured until the early 17th century. Europa was first discovered in 1610 AD by the legendary Italian astronomer Galileo Galilei. Using a rudimentary telescope that he had built himself, Galileo observed 4 tiny points of light orbiting Jupiter. He initially thought they were background stars, but over the course of several nights, he realized they were moving in tandem with the giant planet. These 4 moons became known as the Galilean moons, and their discovery provided the first solid evidence that not everything in the universe revolved around the Earth. However, for centuries after its discovery, Europa remained little more than a speck of light in the telescopes of astronomers. It was widely assumed to be just another cold, dead rock drifting in the freezing depths of the outer solar system, much like our own moon, but covered in a permanent layer of frost. The true nature of Europa only began to reveal itself in the late 20th century. In the early 1970s, the Pioneer 10 and 11 spacecraft passed by Jupiter, providing our first close-up glimpses of the planet and its moons. These early missions were followed by the Voyager 1 and 2 flybys in 1979 AD, which completely revolutionized our understanding of the Jovian system. When Voyager captured detailed images of Europa, scientists were stunned by what they saw. Instead of a heavily cratered surface like our moon or neighboring Callisto, Europa's surface was incredibly smooth, highly reflective, and extremely bright. It was clearly covered in a thick layer of water ice, but it was crisscrossed by a breathtakingly complex network of dark, intersecting lines, ridges, and bands. The lack of impact craters was an incredibly important clue. In a solar system filled with flying debris, any ancient planetary surface should be densely pockmarked with craters from billions of years of asteroid and comet impacts. The fact that Europa had so few craters meant that its surface was remarkably young, perhaps only 40 to 90 million years old, and was constantly being reshaped or repaved. Something highly dynamic and energetic was happening on this distant moon. The mystery deepened significantly in the 1990s when NASA sent the Galileo spacecraft to orbit Jupiter and study its moons in detail. For 8 years, the Galileo probe orbited the giant planet and made multiple close, targeted flybys of Europa. The data returned by this mission changed everything we thought we knew about the icy moon. The most critical piece of evidence came from the spacecraft's onboard magnetometer. Jupiter has an incredibly powerful magnetic field, and as Europa orbits through this immense invisible structure, Galileo detected a secondary induced magnetic field emanating from the Moon itself. The only logical explanation for this specific type of induced magnetic signature is the presence of a vast global layer of electrically conductive fluid located relatively close to the surface beneath the icy crust. In the frozen expanse of the outer solar system, the most abundant and likely conductive fluid is a highly concentrated, salty liquid water ocean. This subsurface ocean is the primary reason why Europa has become the premier candidate for finding alien life. Based on the magnetic field data and complex models of the Moon's interior density, scientists currently estimate that Europa's outer ice shell is anywhere from 10 to 15 miles thick, and beneath that protective icy armor lies a liquid water ocean that could be 40 to 100 miles deep. If these scientific estimates are correct, Europa's hidden ocean contains more than twice as much liquid water as all of Earth's oceans combined. This is a staggering realization that completely shifts our perspective. A moon that is slightly smaller than Earth's own moon holds a global ocean of unimaginable volume and depth. Water is the fundamental solvent of life as we know it. It facilitates all the necessary chemical reactions, transports vital nutrients, and provides a highly stable environment for complex organic molecules to interact, combine, and eventually evolve. Without liquid water, biology, as we understand it, simply cannot function. Finding a vast, persistent, and ancient body of liquid water elsewhere in our solar system is the ultimate holy grail of modern astrobiology. However, astrobiologists know that water alone is not enough to spark or sustain biological life. For a truly habitable environment to exist and persist over geological timespans, three key ingredients are universally required: liquid water, essential chemical elements, and a reliable source of energy. We have already established that Europa possesses an extraordinary abundance of water. The next crucial requirement is the right organic chemistry. Life on Earth is fundamentally built from 6 primary elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements form the necessary building blocks of amino acids, proteins, and DNA. The prevailing scientific consensus is that Europa, like the rest of the solar system, coalesced from the primordial nebula of gas and dust some 4.6 billion years ago. The essential building blocks of life are actually relatively common throughout the universe. They have been consistently found in the icy hearts of comets, the dusty, rocky bodies of asteroids, and even drifting in vast interstellar clouds. Over billions of years, Europa was undoubtedly bombarded by countless comets and meteorites carrying immense payloads of these crucial organic compounds. Furthermore, the rocky mantle beneath Europa's deep ocean is believed to have a composition somewhat similar to Earth's own mantle, meaning it likely contains all the necessary minerals, salts, and elements to support biological processes. The slow, gradual dissolution of these minerals from the rocky seafloor into the water over billions of years would inevitably create a nutrient-rich chemical soup perfectly primed for life. The final, and perhaps most complex, requirement for life is a continuous and usable source of energy. On Earth, the vast majority of the biosphere is powered by the sun. Plants, algae, and cyanobacteria use the process of photosynthesis to convert abundant sunlight into stored chemical energy, forming the massive base of a global food web that supports everything from tiny microscopic insects to massive blue whales. But Europa is located more than 500 million miles away from the sun, receiving only a small fraction of the solar energy that Earth enjoys. Even more challenging, its global ocean is completely buried beneath miles of solid, impenetrable ice, plunging the water into eternal, freezing, pitch-black darkness. Photosynthesis is completely and utterly impossible in the European Ocean. If life exists in those dark depths, it must be powered by a completely different kind of engine. The answer to this profound energy puzzle lies in a physical phenomenon known as tidal heating, which is constantly driven by an intricate gravitational dance. Europa does not orbit Jupiter in isolation. It is caught in a perpetual orbital resonance with its neighboring moons, Io and Ganymede. For every one orbit that Ganymede completes around Jupiter, Europa completes exactly 2, and the highly volcanic moon Io completes exactly 4. This precise rhythmic alignment means that the moons frequently line up, exerting a strong gravitational tug on each other and forcing their orbits into slightly elliptical shapes rather than perfect circles. Because Europa's orbit is elliptical, its physical distance from Jupiter constantly changes as it completes its journey. When it is closest to Jupiter, the giant planet's immense gravity pulls harder on the moon, stretching its solid body. When it moves farther away, the gravitational pull weakens and the moon relaxes back into a more spherical shape. This constant, rhythmic stretching and squeezing creates immense internal friction deep within Europa's rocky mantle and its thick ice shell. This friction generates a tremendous amount of heat, a process physically identical to rapidly bending a thick metal wire back and forth until it becomes hot to the touch. This internal tidal heating is the crucial mechanism that keeps Europa's ocean from freezing solid into ice. But its implications for potential biology go far beyond just providing liquid water. This immense internal heat must eventually escape from the moon's rocky core upward into the overlying ocean. On Earth, when intense heat from the mantle interacts directly with seawater, it creates hydrothermal vents on the deep ocean floor. These vents are fissures in the planet's crust, where geothermally heated water, sometimes reaching hundreds of degrees, erupts into the freezing ocean water, carrying with it a massive payload of dissolved minerals and gases from the interior. When deep-sea hydrothermal vents were first discovered on Earth in 1977 AD, it completely revolutionized our understanding of biology and the limits of life. Scientists were shocked to find entire thriving ecosystems teeming with bizarre and wonderful creatures living miles below the surface in complete darkness under crushing immense pressure. These ecosystems do not rely on sunlight or photosynthesis at all. Instead, they are entirely powered by chemosynthesis. Specialized bacteria at the base of this lightless food chain extract energy directly from the chemical reactions between the hot, mineral-rich vent fluids and the cold, oxygenated seawater surrounding them. If Europa possesses a rocky core that is in direct contact with a liquid water ocean, and if that core is being actively heated by intense tidal forces, then it is highly probable that hydrothermal vents exist on the European ocean floor right now. These vents could easily provide the exact same type of chemical energy that sustains complex deep-sea life here on Earth. They would act as hot, nutrient-rich biological oases in the freezing, dark depths of the moon, serving as the perfect environments for life to originate, evolve, and thrive over billions of years. The striking similarities between the deep oceans of Earth and the potential deep oceans of Europa make it incredibly tempting to imagine similar forms of extremorphal life swimming in those alien waters. However, there is another critical component to this biological energy equation: For chemosynthesis to work efficiently, especially to support more complex multicellular forms of life, there needs to be an energy gradient, which is a chemical imbalance that organisms can exploit to generate energy. On Earth, this vital gradient is created by the reaction between reducing compounds coming from the volcanic vents and highly oxidizing compounds present in the seawater, primarily dissolved oxygen. Where would an enclosed, ice-covered world like Europa get these necessary oxidants? The fascinating answer comes from Jupiter's incredibly harsh radiation environment. Jupiter possesses the strongest magnetic field of any planet in the solar system, trapping charged particles and accelerating them to phenomenal speeds, creating deadly radiation belts. Europa orbits directly within the heart of this intense radiation environment. The surface of Europa is constantly bombarded by high-energy electrons and ions, creating a deadly surface environment that would instantly destroy any unprotected organic life forms. But this intense radiation also performs a highly crucial, life-enabling function. It continuously splits the water molecules in the surface ice into hydrogen and oxygen. The much lighter hydrogen quickly escapes into space, leaving the heavier, reactive oxygen behind to become trapped within the icy crust. This dynamic creates a highly fascinating chemical battery. The surface of Europa is continually enriched with oxygen, hydrogen peroxide, and other oxidizing chemicals created by the relentless radiation, while the deep ocean floor is simultaneously enriched with reducing chemicals erupting from potential hydrothermal vents. If these two extreme chemical environments can somehow mix, it would create a powerful and sustainable chemical battery capable of sustaining a robust and potentially complex biosphere. The primary challenge is getting the precious oxygen from the irradiated surface down through miles of solid ice and into the liquid ocean below. Fortunately, Europa's surface is incredibly active and chaotic. The constantly shifting ice shell creates massive cracks, towering ridges, and wide regions of chaotic terrain where the ice is violently broken, tilted, and jumbled. Scientists strongly believe that this ongoing geological activity, constantly driven by tidal flexing, could allow the ice shell to slowly churn over time. Convection currents within the warmer, deeper layers of the ice shell could slowly transport the oxygen-rich surface ice down into the ocean over millions of years, continuously delivering a steady, life-giving supply of oxidants to any biological organisms waiting in the dark below. The compelling evidence for Europa's active geology is highly visible all over its scarred surface. The Moon is completely covered in a complex, intersecting array of lineae, which are long, dark fractures that can stretch for thousands of miles across the white ice. These massive cracks continuously open and close as the Moon is squeezed and stretched by Jupiter's immense gravity during its orbit. As these fissures open, warmer, slushy ice or even liquid water from the deep ocean below may well up to the surface, bringing dissolved salts, minerals, and complex organic compounds with it. When this deep ocean material is exposed to the harsh vacuum of space and Jupiter's intense radiation, it undergoes chemical alterations and turns a distinct reddish-brown color, which is exactly why Europa's massive cracks appear so dark against the bright, reflective white ice. Studying the exact chemical composition of these dark, reddish-brown deposits from orbit could provide astrobiologists with a direct, unobstructed window into the chemistry of the hidden ocean, without ever having to undertake the monumental engineering challenge of drilling through the incredibly thick ice shell. In recent years, detailed observations by the Hubble Space Telescope have provided even more tantalizing and exciting evidence of Europa's active, dynamic nature. Astronomers have repeatedly detected what appear to be massive plumes of water vapor erupting from the Moon's surface, occasionally reaching hundreds of miles into the vacuum of space. If these towering plumes are fully confirmed and are truly originating directly from the subsurface ocean, it would represent an absolute game-changer for the future of planetary exploration. It implies that Europa is actively venting the contents of its ocean into space, essentially offering humanity a free biological sample. A properly equipped spacecraft flying directly through these massive plumes could capture the ejected material in real time and analyze it for complex organic molecules, amino acids, or even the direct chemical signatures of life itself, completely bypassing the immense and perhaps currently impossible technological challenge of landing a probe and drilling through a 10-mile thick shield of solid ice. The profound and undeniable potential of Europa has led major space agencies around the world to prioritize its exploration above almost all other targets. NASA is currently finalizing the development of a massive flagship mission called the Europa Clipper, specifically designed to conduct a detailed, comprehensive reconnaissance of the icy Moon. Scheduled to arrive in the Jupiter system around 2030 AD, the Europa Clipper will not land on the dangerous surface, but it will perform dozens of highly complex close flybys, swooping in extremely close to gather high-resolution data and then rapidly retreating to escape the worst of Jupiter's damaging radiation belts. The spacecraft will carry an incredible suite of sophisticated scientific instruments, including powerful high-resolution cameras, highly sensitive mass spectrometers to map the surface chemistry in detail, and a massive, powerful ice-penetrating radar system. This radar will send radio waves deep into the ice shell, bouncing off internal structures within the ice and, most crucially, reflecting off the boundary between the solid ice and the liquid ocean below. This will finally allow scientists to determine the exact thickness of the ice shell globally and pinpoint specific regions where the ocean might be closest to the surface, perhaps where the ice is thin enough to allow for future subsurface exploration. Furthermore, if Europa is actively venting plumes when the spacecraft arrives, the Clipper's instruments are perfectly designed to fly directly through them, tasting the chemical makeup of the ocean and relentlessly searching for the building blocks of alien life. In parallel with NASA's ambitious efforts, the European Space Agency has successfully launched the Jupiter Icy Moons Explorer, commonly known as JUICE. While the JUICE mission will focus a significant portion of its primary efforts on Europa's larger sister moon Ganymede, it will also perform multiple crucial flybys of Europa, providing highly complementary scientific data and helping researchers fully understand the icy moon in the broader, complex context of the entire Jovian system. These massive, multi-billion-dollar missions represent the next great leap in the field of astrobiology. They will decisively lay the critical scientific groundwork for bold future missions that might one day attempt to land gently on the treacherous surface, safely sample the reddish-brown organic material slowly seeping from the deep cracks, or perhaps even deploy advanced nuclear-powered cryobots designed to slowly melt their way down through the miles of solid ice to eventually release autonomous robotic submarines into the dark, uncharted alien waters below. The ultimate discovery of biological life on Europa, no matter how small or seemingly insignificant, would undeniably be a massive, paradigm-shifting event in human history. If we were to find even a simple, single-celled microbe swimming in that distant, dark ocean, it would profoundly tell us that the genesis of life is not a miraculous, incredibly rare one-off event that somehow only managed to happen on Earth. It would strongly suggest that biology is a natural, perhaps even inevitable consequence of the universe whenever the right chemical and physical conditions are present. If life can successfully arise twice in the exact same solar system on two completely different types of planetary bodies, then it stands to reason that it must be incredibly abundant throughout the cosmos. The universe would instantly transform in our minds from a vast, sterile, empty void into a thriving, deeply interconnected biological tapestry, fundamentally changing humanity's perspective on our place in the cosmos forever. While the rusty red planet of Mars will always hold a very special and important place in our ongoing exploration efforts, it is ultimately a world of the distant past. If biological life ever existed on Mars, it likely died out billions of years ago when the small planet lost its protective magnetic field and its thick atmosphere, leaving behind a frozen, highly irradiated, barren desert where only fossilized remnants might remain. We are largely searching for the ghosts of life on Mars, but on Europa, the situation is vastly different. We are searching for living, breathing, active ecosystems. We are searching for a massive global ocean that is actively churning with immense chemical energy today, right at this very moment. The incredibly thick ice shell that totally hides this ocean is not merely a frustrating barrier, it is a vital, protective shield, keeping the precious liquid water highly stable and effectively sheltering the delicate biological environment from the deadly, destroying radiation pouring down from above. Beneath that fractured, shifting, frozen surface lies a massive, lightless abyss of truly endless possibilities. The dark, salty, churning waters of Europa constantly call out to our innate human curiosity, challenging us to build the tools, the technology, and the spacecraft necessary to reach out across the vast darkness of the solar system and touch the unknown. As we eagerly stand on the threshold of a totally new and exciting era of space exploration, Europa steadfastly remains our greatest hope, a brilliant beacon of potential biology shining brightly in the cold, dark depths of the outer solar system.